My topic for discussion is video compression and its concepts and challenges, and again, what are the standards that we use for video compression. Now, this is an overview of the topics that I am going to cover. Then, what are the major techniques or why we are going for video compression? That is, what is redundancy reduction techniques. Then, we will have a basic video codec, that is encoder and decoder structure. Then different types of frames, and again different types of video coding, that is we are having intra-coding and intercoding. We will see those terms later. Then again decoding part, and again we will end up our discussion with introduction to video coding standards. Now I can say that video is nothing but sequence of frames, and the major attributes of any video is height, width, frame rate and pixel values. So in an image you will be having width as well as height, and again in video there is number of frames per second, that is what you mean by frame rate, and pixel values, that is the intensity values of each and every pixel. Now in a 1 second video normally we will have 24 frames or 30 frames per second. Then first we will see these are the major attributes and why we need compression. That's the next point of discussion. Then I'll be starting with a simple point, that is nowadays this 720 into 480 we will not be normally using. So whenever we are having a frame of size 720 by 480, the number of bits that we will be having will be those length, that is width into height. Then again we will be going for representing the each and every pixel value with 8 bits. Then we will be having RGB components, means 3 such fields there. So basically 720 into 480 into 8 into 3. So that much number of bits will be there, and if it is byte it will be 1/8 of that particular one. So for a simple frame, that is we can say for a simple image, the size is 8.29 MB, or if it is capital B it is 1 megabyte. So this here small b is bits per only. Now when you move from such a frame to, say, when the resolution is full HD 1920 into 1080, there you can see that the size is almost, say, 1.492 GB and the gigabits, and 1/8 of that will be the size. So that is why we are going for video compression. That is, say for a 1 second video, if this is the size, then you can imagine what will be the amount of data that will be there for a 1 hour video or a 2 hour video. So without compression we will not be able to proceed, and why we are going for this particular one is to fit it into storage devices or transmit it using the available bandwidth. Again, as per a latest study by Cisco, nowadays, that is by 2020, around 90% of the network traffic will be just because of this video. Nowadays everybody is going with higher and higher resolutions. This full HD is there. Again we will be having videos like 4K, 2K, etc. So different types of image resolutions, and again there you can see that as the size increases, that is, say, the number of bits or bytes will be dependent on length and breadth. When you increase the length and breadth, those values will be multiplied by 24. Again when the number of frames is 30, again for a 1 second video you will have to multiply it with 30. So as the resolution of the video increases, or nowadays as the resolution of the imaging techniques increases, the size of the video is increasing by that much, and that is why we are going for, we need better compressions, and each and every video compression standard basically upgrades the previous compression standard, and by default normally the procedure is it must be able to compress, that is double the compression rate without having any reduction in quality. Now when we go for video compression, say basically we are going for reduction of redundancy, and those redundancy may be spatial redundancy or temporal redundancy. Spatial redundancy means within a frame itself we will be having redundant information. For example, if it is a small board, a picture is having a border or something like that, there you have similar regions there. That is, when it is a smooth region, almost all area are having the same pixel values. So you can go for the reduction of such redundancy, then it is called spatial redundancy. And the prediction strategy for spatial redundancy is intra prediction, that is within the frame. Intra means within the frame, and inter means within successive frames. So whenever we are going for video, we are having 30 frames per second. So in a second, if you are capturing just like this video, the nearby frames will be highly correlated, because there may not be having that much background change or something, only there may be slight movement. So successive frames will be highly correlated. So that will be the main topic of this temporal redundancy. And perceptual redundancy means, say, our eyes are, that is, may not be able to capture all those changes. So again, if those information that our eyes are not able to capture, if we can go for reducing such redundancy, perceptual redundancy is there. That means even if by reducing say the bit means the number of bits by 50% or maybe something, that is if you compress by 10 times or 100 times, even if you are not able to detect those changes, that is visual quality, that is norm for a normal human being, if he is not able to visualize those changes, means there is no meaning in keeping all those information. So we can compress it by many times. Then statistical redundancy is basically coming to the coding part. So that is related to communication part. I will not be going into those details. So basically within the frame, then across frames, then we will be having those perceptual redundancy, that is relevant information related to our eye will be reduced. Then as I explained earlier, these two things, that is spatial is within the frame and the second one is time based. Now we will see spatial redundancy means within a frame. So here we are having a TT, that is a video or frame of a particular player who is playing table tennis. So here you can see that this region is highly correlated with this region. So here you can see that in video coding we will be dividing, or still image compression, we will be dividing that frame into blocks of equal sizes. That size may be varying from standard to standard. For example, if it is a 720 into 480 frame, we can divide it into blocks of 8 by 8 or 16 by 16, such that. So we will be doing all these operations on a block level basis. So this is one example of a block, and this is another block, and those two blocks are there. So we will be coding these blocks one by one. That is the basic principle. Again, once we code a frame, we have the next frame also. That is, we are going for the coding of the second frame. Before that, we are having we might have coded the first frame. So when we have the previous block available there, then for the prediction of the current frame, what we do is we will be generating a prediction based on our previous frame information, and that value, that is, we will be going for the subtraction of that value from the current frame. That is, previous frame's value will be subtracted from the current frame's value, or a prediction based on the previous frame will be subtracted from the current frame. Then we will be getting the error frame, and that frame we will be coding. So when we go to the error frame, means those values will be very, very small. Here you can see that we are having two successive frames, and when you go for the subtraction, most of those values are converted to 0. That is, when you perform the subtraction, those two regions are exactly matching. That means the difference will be 0. So that is why that particular region is coming as black. So in images, 0 represents black and 255 will be perfectly white. So now when you go for coding all this information, means we are having most of the pixel values are 0 when you go for the residual coding. So that is the advantage of having this difference frame that is being used for coding. Then again, perceptual reduction, I said that all those informations relevant to our eye will be discarded. Here you can see that, say, those original image, and again when we are applying those when we are reducing those irrelevant information, again we are not able to visualize what is the change between those two frames. So that is basically there. Then in statistical redundancy, we will be going for entropy coding, and again there are variable length coding and all those strategies there. So that I will not be going into detail, because that is related to electronics and communication. So now basically some of the terms that I would like to explain related to video compression. So whenever we say a codec, we will be basically referring to encoder and decoder. Then here you can see that in between this encoder and decoder, we have the channel, and sometimes we will be storing those information. So we may be having those, capturing those information, then encode it, and maybe storing it, or maybe transmitting it, and at the other side we will be having that decoder part. Now we will see the basic codec structure. So here we have the original frame, then we have the video encoder, and this is the coded stream is sent to the channel, and this side is decoding side. So whenever we are having a frame, that frame will be sent to the encoder, that is for the coding purpose. Once that coding is done, that will be stored somewhere for future reference. That is, when you are coding the second frame, you may be referring to the first frame, and when you are coding for the third frame, you may be referring to the previous frames. So for that purpose, we are keeping this buffer. And at the decoder side also, we are having that particular buffer. Then we should be able to mimic the operations that we performed at the encoder at the decoder side. Then only we will be able to replicate that particular process or perfectly reconstruct the video. That is why we are keeping these buffer values there. Now basically the block diagram of an encoder. Here you can see that, say, first we are going for that conversion. Say in most of the cases we will be going for conversion from RGB to some other formats, maybe YUV, because in RGB we are giving equal importance for R, G and B components. That means all the components are having the same weightage, or we can say. But when you go for YUV, means YUV is basically luminance component and chrominance component, and our human eye is more sensitive to luminance changes and less sensitive to chrominance changes. So the main property, that is, if we are able to subsample the chrominance component, that means discard some of the chrominance component, we will be able to reduce the number of bits. So if you want to do that particular one, you should be doing it on a less important thing. So when you convert from RGB to YUV, the Y information is more important, and this UV part, that is chrominance information, is less sensitive, and that is the advantage. You can go for subsampling 4 to 0, 4 for something like that. Those different subsampling means, say we will be taking, say, whenever that is for 4 luminance components, we will be taking only 1 chrominance component or 2 chrominance components. The rest we can discard, and at the decoder side we will be interpolating the one of the samples that we retain to generate those 4 samples. So that is the basic concept of subsampling. Now here we are converting it. Again we have 3 components by UV. Then again always we perform that, generate that residual. So original will be, that is a prediction, will be subtracted from the current frame to generate. Then we will be applying transformation techniques. That is, here in most of the cases we will be using discrete cosine transformation for transforming that particular things. Again that is followed by quantization. Quantization means basically that is reducing the size. So we will be dividing the entire set of pixel values with another matrix. That means each and every value will be divided with the value that we will be specifying. So based on the value that you set for the quantization, you will be having images of different qualities. Say when you view a particular video or something, there you have different quality options. Basically quality option means when you change the quantization parameter. So if I have the pixel value as, say, for example 170, then if the quantization parameter value is 25, so I will be dividing 170 by 25. When I increase the quantization parameter value, for example if it is 90, the value will be there. When you divide it, the value will be coming approximately as 2 only, rather than the previous cases. Then when you perform those DCT, actually this transformation in the transform domain, most of the pixel values will be converted to 0. Only few pixels, that is only for few coefficients we will be having those values, and then we will be applying the entropy coding techniques. Now this is the encoding part, and again at the decoder side also is there, and this particular part is, that is, motion compensation and motion estimation is basically related to interprediction, because between successive frames we are estimating a prediction. So that is, we will be generating, that is, how much movement is there between successive frames. That is basically motion estimation. Then once we are able to estimate that particular motion, we will be doing the motion compensation. I will show you a video of how that particular thing is computed. Then again at the decoder we will be doing the operations just in the reverse order. So we were having that the last option was entropy coding. So first option will be decoding of those things, that may be Huffman or any other things. Then inverse quantization. Then again inverse transformation and all those things. Now basically we will be dealing with different types of, that is, although we are having successive frames there, we will be classifying them into different groups like high frames, P frames and B frames. I frame, that is, here you can have a set of videos there. So I frame is a frame, IntraFrame, that is coded independently, that is without referring to any other frame. So we will be having those I frames coming there. Then we have the P frame, that is predictive frame. So they will be referring to I frames. And B means bidirectional predictive, that is it will be referring to more than one frames. So what is the advantage is that, say this particular frame may be, this P frame may be referring to this I frame, and this particular B frame may be referring to this P frame or this I frame. So that can also happen. Now, say in the iframe, that is we will not be referring to any other things and we will be compressing it. So it is basically a reference frame and can be used to predict the pre-frame, P frame immediately following it. Now say in P, that will be referring to I, or P may be referring to some other P also. So a P frame can be referring to some other P frames also. Now when you come to B frame, it will be referring to more than one frames, and that may be P or I, or maybe between P and P. So when you refer to some other frames for the prediction, that is you will be having B frames or P frames. And again here, say for example, here you can see that those frame numbers are 1900. It is starting from 99 only. I am not considering the first 98 frames. All those frames are in sequential order, but that is the display order. Those frames, since we are dealing with B frames and P frames, the coding may not be in this particular order. So first we will be coding the frame, that is I frame, that is 100th frame. Then we will be having this 102, because it is referring to only this 100th frame. Then we will be having this B frames that may be referring to I and B frames. So whenever there is dependency is there, the frame that is to be referred should be coded first, and at the decoder side also that should be decoded first. So the order at the decoding order will be 100 followed by 102, then followed by 99, 101, etc. So that means out of order will be there. That is, we are making use of those interdependency to the maximum. Then again, as I explained, we are having the raw frame will be divided into blocks of smaller sizes, and each and every block will be treated for those coding and all those informations. Now, in non-intra-frame, that is interframe coding, say there you can see that you are having two pictures. What is the difference is basically these two persons sitting are standing close to this particular tree, and there that movement is there. So almost all other things are constant. That is, tree will be constant, then the background will be constant. The only difference is in between their movement. So successive frames we will be able to refer to the previous frame and code all those things, informations. Now how you will estimate that motion? In interprediction, we will be estimating that particular motion. There you can see that each and every block is there, and this particular thing will be also clear when I explain. I will be showing that particular video. You can see how we will be estimating those information. Again, once we estimate all those things, we will be having that decide frame and subtracted frame. Again, all these things I will be skipping. I need to one more minute for just showing the video. Now in the current frame, this is the reference frame that is being already coded. So a portion of that particular frame is taken, and we are searching for the nearby region, that is exact position and its nearby region. There you can see that we will be first coming to the exact position, then the regions near to that particular block will be checked, and we will be coding that particular one. Again, when that block is coming, automatically coming here, then its nearby regions are searched. So that searching distance depends on basically what value you are setting there. So that means that is a trade-off between computational complexity and runtime and all those things. So this is basically predictive coding scheme. So each and every block of the current frame will be compared with the reference frame, and we will be having those motion compensated frames coming there. Here also, how those two successive frames, say when you are getting a black, means those two regions are exactly matching. So you are subtracting it and you are getting the residual frame. And whenever you are having those movement, there you can see when you are coming to the second row of there, some form of information is coming here, and again here you can see that there is some movement there, and that is why you are having all those information coming there. Otherwise it will be perfectly black. Whenever you are having perfect matching, subtraction will be yielding 0, and you will be having those values, regions will be represented as black, perfectly black. So that is the basic concept of this residual coding. And again, one frame, for the coding of one frame, we may be referring to more frames, that is frame number 1 or frame number 2. And sometimes whenever you are having meeting such conditions like threshold or something, perfectly matching means we will not be checking for further checking. So you may be referring to 1 frame or 2 frame or more than 2 frame, that also can happen. So reference frames may be more in number. So I will be concluding this session, and